So I can glad I finally join and become one of the speakers for this MIFF AI workshop. Cool, then I'll start my talk then. So today I think because the whole talk will be like 2 hours long, but we only have 35 minutes. So instead of details, I will just pick up 2 case studies, maybe one in ophthalmology, one in dermatology that will cover the main cohort of the audience interest. If we have time, we can cover a bit story from the neurology AI as well. Cool. All right. So maybe I'll start with why and what's the motivation I founded and established the Monash Medical AI Group, and why that I've been working in computer vision, robotic vision, medical imaging for a while. Why choosing medical AI as my main research topic in the future? So a few numbers you can probably see from the graph from the World Bank data. So the first is the median age of our human being largely increased, right? So which means our society is entering into the aging society, which means there can be more elderly people and less young people. I mean, the relative proportion, right? And in terms of the birth rate across the whole world, in terms of the number of children per woman after World War II, the number is significantly dropping. So for example, in China or in some East Asia countries like Japan, Korea, the birth rate is about one couple only has 1 to 1.2 kids. If we keep doing that, you can imagine every 2 generations, our total number of population is going to drop around by 50%. So what you can expect in the future is if we are entering into a population aging society, we first need a more comprehensive public health response. That's for sure, because we have more elderly people in the society, and to some extent burden society and to the dependent as well. And there are many more things we need to consider, for example, the social and economic factors. So in our generation, and maybe my kids, their next generation, they are facing the era, they're gonna, for example, support the elder people just by themselves, rather than like our last 2 generations. Normally they have lots of siblings, lots of cousins. So it's going to be different story. So if you check what's currently happening in Korea in the right bottom picture, as you can see, there are far more elder people compared to the young kids in the society. So these are just one illustration. And in terms of the healthcare expenditure is also going up in terms of the number percentage out of GDP, how much money we spend country-wise. If you can see the left-hand side, the United States, the number is going rocket high, and there's no momentum stopping and drop down that proportion. It's just keep climbing up. And on the right-hand side, I'm just showing because the recent advanced in our medical technology, our life expectancy is also being increased. So in Japan, South Korea, United Kingdom, now the life expectancy is over 80 years old. And the rest of the world, developing countries, they are also growing. So in terms of the impact on healthcare system, I believe most of the people joining today, they are either working in directly the healthcare industry, or you are clinicians, doctors, or medical AI engineers, right? So in the future, we definitely need more healthcare resources in terms of the capacity, the number of beds, ICU beds, and also the quality of the medical service. But on the other hand, if you wanted those 3 numbers to keep climbing up, you can imagine in terms of the healthcare budget, we also need to do lots of work, right? How we can control this and how we can solve this problem. There's no solution like we train more nurses, more doctors on the market. I don't think that's going to solve the problem, because in the aging population society, the difficulties we're facing, they grow exponentially, not linearly. If they grow linearly, we can meet up with the expectation by training more clinicians and doctors, right? So a quickly summary would be the world now have been going through an important demographic transition from young to increasingly aging populations. and life expectancy has increased rapidly since the age of Enlightenment since early 19th century. So the global average fertility rate is just below 2.5 children per woman today. So over the last 50 years, the global fertility rate has halved. And you may imagine this number is going to keep going down in the next 20, 30 years. And the last point is the global trends in healthcare expenditure mask a great deal of heterogeneity, right? So do you think the technology can actually maybe alleviate the difficulties or the issues I just raised? Maybe possible. One trend we can't ignore in the recent 5, 10 years, it seems like, especially in the medical domain, everything is going to digitalized. For example, all the medical data, the EHR, EMR, the clinical reports, they are now handled by a technology called NLP, so natural language processing. And the radiology data, they used to be interpreted using the physical, the slides. Now everything goes into computer. And there's an research area called CAD, computer-aided diagnosis, to help clinicians, radiologists dealing with those information. And more medical data, since they are digitalized, so now they can be linked. So you are hearing more and more modern words, maybe like machine learning, AI model. They are multi-source, multi-modality, multi-cohorts, multi-sites, and all these data can be linked because of data digitalization. And we can now carry out those sensors not by ourselves, not just only in the ICU. So we can get 24/7 pulse data, physiological data, element analysis, for example. Because so Facebook, the social media, is the #1 data generation every single day in our life. The medical data will be the world second. So more and more data can be generated from the hospital, from the wearable devices you're wearing every single day. And there's one graph there, maybe it's too small for you, but through the whole lifetime, you're going to generate 8 terabyte data. So that means 1 terabyte equals to around 1,000 gigabytes. So you can see the number. Okay, I'll just skip those two. I just want to show our human space in terms of the medical technologies keep going up from understanding the diseases more for the religious purpose. Now people are going understanding by autonomy. Now we can now start to investigate and understand the disease, the pathway, the efficacy of the drug usage through the data. And the medical data, they comes from various different kinds of forms, from X-ray to CTA data, to PET-CT, to retina, to dermatology, to EHI, EMR, all kinds of data. I don't think even a well-trained, very senior doctors can handle all the data from one patient simultaneously. It's impossible, given that now the genome sequencing is becoming cheaper and cheaper. I don't think anybody can interpret 3 billion pairs in a very short period of time, right? But can the machine help us to do so? So there are recent some cover stories from the Nature article you might have heard about, for example, some skin AI and technologies, and some brain synthesis reconstruction to help using machine learning model to understand the brain, and also the DeepMind from Google. They have created a model called AlphaFold, which can nearly perfect predict the structure of the protein. So this is very important. I think marks another milestone with using the technology to understand what's happening inside our body. So that's the whole. I've been talking for maybe 10 minutes. It's a risk to reach to one conclusion. Is that's the reason why I think medical AI plus digitalization plus clinicians will be the future. So that's why the reason I founded Monash Medical AI. So we believe AI technology plus medical will bring better healthcare into this world. And our mission is obviously very clear, to deliver high quality healthcare service through world-class research with our industry partners, AirDoc, iTelligence, Sarah, and healthcare providers. Okay, now we can jump a bit what we have been working on. So we break our group's research topics into 3 levels. to the very bottom level to the machine learning theory, knowledge discovery, the neural network architecture search, the open set theory study to support the medium level of applications like model interpretation and adaptation of the model, vision, NLP data, learning together. Then on the very, very top, it can get all the nutritions from the bottom two levels, then being we develop the end technologies to skin, diagnosis, to brain, to eye disease diagnosis, to different sensors, signal interpretation models, and medical implementation sensors to understand what's happening inside our body. Okay, so to start with, I think we can start our first case study. I just skip these ones. It's basically showing our research philosophy, how we start our topic. Okay. So the first, what do we say? We focus is called real-world diagnosis and prognosis. So why I particularly meaning the real world? It's because many of the machine learning or medical AI technologies in the last 20, 30 years, we say it's more like the lab world diagnosis. So these pictures, especially middle one from MD Anderson, it gives you an illustration of a very clean, controlled lab environment. So when we get diagnosis on these data, we normally expect them that it's controlled, noise-free, no disturbance from the surrounding environment. But however, in the real world, you might have read the story from Google, especially if you're working in the ophthalmology. So Google's medical AI model was super accurate in the lab, but real life was a different story. That's because in the real clinic, they did a large-scale study in Thailand. They found out different camera models. So the blurry of the image, the artifacts from the image they got, creating lots of issues. So results in pretty bad performance job in term from the AI model. It didn't match what they got from the lab, right? And imagine the real world scenario. Of course, you're gonna have overcrowded hospital. You don't have 30 minutes taking a good picture that run into an AI model. Everything needs to be fit into a medical pipeline. There's so many factors you need to consider, and everything will be very crowded, very noisy. So how we can create a medical AI model or a systematic way to solve this problem? I might use the example of our recent study with the Center for Melanoma Imaging, which worked together with the Australian Center of Excellence in Melanoma Imaging and Diagnosis. So the overview, it's pretty straightforward. We want to use diagnostic intelligence health service evaluation informatics to help solve the problem of people dying from skin cancer or melanoma. So in order to achieve that, we have 3 milestones we want to reach in the next 5 to 10 years. So if you can see from the left-hand side, so the level 1, milestone 1, is we first leverage the SOTA with state-of-the-art AI technology research and informatics infrastructure to establish the multidisciplinary research, is to combine a hybrid team with clinicians and technology scientists together and apply AI technologies, see what we can achieve, what is the edge of the computing of the technology. And second part is once we have a very good lab model developed, we want to really trust getting into the pipeline is very important. So we implement AI model to understand the impact or the potential impact it has on clinical decision making. A purely good AI model standalone doesn't mean anything. It has to work together with the clinicians in the real pipeline, real lab. And the third will be champion reduction in the overarching burden, mobility, and mortality. So on the right-hand side is what kind of data we take and what kind of approach we take. So as you can see, the data we include not just telehealth dermoscope images, also including a 3D vector machine taking your full body, tracking every single lesion. And then we also, in the future, we're going to take in the genomic sequencing, hopefully the variance points as well into the model, and also the family history or the metadata or behavior information, and to build a hybrid or a multimodal model. So these are the work we have done so far by using AI technologies. So we have, you don't need to understand the details in the graphs, but we have built up different AI models, try to solve the early detection problem, understanding of the hierarchical label of the disease, because of many disease doesn't go straight forward to the cancer. There's many pathways in the middle. And we also follow the latest concept study of a skin and cancer diagnosis, like the concept of ugly duckling, not looking at single lesion, but instead looking lots of lesions as a contextual information put into a model together, and we do multi-model modality learning. So this is a typical framework for current AI technologies. So on the left-hand side, we're putting lots of annotated lesions into something called deep neural networks or deep learning. Then on the right-hand side is what you get and present a display to the clinicians, segment out the lesions, tell the probability of being a cancer, being a melanoma, and how we get the gathered evidence, how the model thinks it's a melanoma. So preliminary study, and there's also a SMARTY trial currently going on in Australia. Some numbers I can show you quickly. In our very first trial, we have collected around 700 data points, including 592 benign, around 200 non-melanoma skin cancers, and 68 melanomas. So the AI model, what it can reach is for every single referral cases, so we get 9.18 benign versus 1 melanoma. So that number is still not very ideal, right? Because the training model label we got is from the clinicians or dermatologists labeling. So the best performance we got so far by viewing by specialists in the secondary care space is benign, which is 8.7. So the lower the better. There's still lots of false positive going on, as you can see, but it's way better than GP, which is benign melanoma ratio for excision is about 17 versus 1, right? So that result has been published in our recent medical journal. So that's a preliminary study. Then we want to investigate a bit further into the data points. For example, rather than taking a single estimate point of the data, can we take a sequential or longitudinal data together? Since we understand the melanoma cases, they keep evolving, they are growing bigger and bigger and deeper into your skin, into your muscle. So we developed the next generation technology by incorporating multiple snapshots of lesions from different time points into the model. So we have a special learning mechanism called some early knowledge distillation to learn the sequential information, to also incorporate the spatial and temporal information together. So we have recently published some data and performance in the recent IEEE transaction on medical imaging, which is a top journal. So the results has been pretty so far. So I don't have time to present today, but it's much better than a single image. Then we dig deeper to taking the most cutting edge concept, which is ugly duckling sign. As I have mentioned before, is rather than looking at a single lesion evolving, can we look at all the lesions from a patient, see how they change, and how seeing one melanoma or the cancer will stand out with against the other lesions from the body. So that's the key concept. So that the nevi in the same individual tend to resemble one each other, while the ugly duckling, the lesion, which is the real melanoma or the cancer lesion, tends to stick out or look very different compared to the surrounding nevi. So in terms of the technology part, so we want to train a neural network, not just taking a single lesion, but rather than taking a group of lesions together into the model, and not just model itself, but model the correlation between various kinds of lesions. So that's the overall architecture, but 3 main technical innovations. It's okay if you don't understand it, but basically we learned the multi-scale feature from every single image. We put all the image lesions into the model to learn the correlation. And we also use a specific called group contrasted learning to increase the accuracy of the model. So I'll skip the data part, but the performance we've got so far is, I think, 3 percentage better than the baseline. So what we got so far is 86.21, which is pretty good for real clinical usage. Then we also tried further on the hierarchical study. For example, for a skin lesion, we believe for different levels with benign, malignant. But if we go further, then we'll go to SCC, melanoma. So all these kinds of level information, they're information rich. And all the AI models, as you know, you probably heard they're very data hungry. I would say not just only data hungry, they're also label hungry as well. You need to provide very high quality label and also rich information to label as well. So I think by instead of just providing benign versus malignant, we're providing different levels into the model training as well. So what you will see, the output of the model is, previously, if it's a flat classifier, it will be listing out the lesion probabilities like this. Now, if we do hierarchical classifier, we can see 3 levels. First level will be malignant versus benign. Then we go to further deeper and deeper into more fine-grained or granular level of information, which we think will be also important and transparent to the clinicians who is reading the report as well. So they can understand more and they can explain further to the patients and the clients what has been happening inside the model. Okay, so we are currently at step 2. We are doing a trial, a real into the clinical pipeline. So these are the 2 phases. One is active phase, one is a leading phase. So in the active phase, we would really focus on is we put the AI model before the dermatologist or the P looking at the data, and versus after, we're trying to see which way is better. We also take consideration about the personality and their understanding of the AI, and if they accept AI or not, all into consideration to take this trial. Then we figure out if with AI's assistant model, will this hybrid model perform better than just purely human decision making. So this is currently under research. Great. So we'll move into the next part, which is AI research in ophthalmology. So this is a more industry-oriented project with my research partner, industry partner, AirDoc, and Intelligence. So the goals of ophthalmology AI is quite simple. That is because we think, and that has been clinically proven that retina first, of course, is the only place to directly observe vessel and the neurons without invasion, right? And the retina plays an important role in diagnosis and prognosis of chronic diseases such as diabetes. So for some chronic diabetes patients, you will see something called DR, so diabetic retinopathy on the back of the retina. And for some hypertension, you will see some manifestation and symptom on the vessel and artery at the back of the eye, and some potentially coronary artery and heart disease, PD, and dementia, those chronic neuron degeneration diseases. And the retina has direct diagnostic biomarkers for high myopia, which is more common these days for young kids, AMD, glaucoma, cataract, for example. So I think retina is a perfect source, perfect image source to understand so much things what has been happening inside the body. And I think retina plus AI technologies, we can do things not just inside the hospital and outside the hospital as well. So if everything goes well, those can serve very well for the remote region, for the primary care organizations, and inside hospitals if necessary. So the first part is we also break into 3 milestones, 3 levels of goals as well. So first is leverage AI research again and informatics exactly as any other medical AI projects. So second, we partner and provide high quality and regulated scanning services for in and out patients. So I mentioned regulated specifically is for products or service like this. You want it to be trusted and backed up by the clinicians, backed up by the FDA, backed up by the TGA. Hopefully it's category 3, which is the topest category. And the last part would be discover early and better manage chronic diseases inside the community, because many healthcare economists these days have already proven that. So preventive medicine versus treatment medicine, preventive medicine actually can save lots of financial budget from the healthcare spending. So there's one study, I think AirDoc has done a very good study, a national real world evidence study for the AI model. So the AI model is basically the trained AI model by using all the retina information. Then the model is able to tell if it's a DR, AMD. So basically they have trained a model and for, I think, 17, 14 different common eye diseases. And their methods has been trained by using around 200,000 color fundus data, but cover lots of hospitals. But really, I think it's a real world study is because it derived from 16 clinical settings with different disease distributions. And the model called CARE care was internally validated from 35 real world settings across China, where it must be adopted, including 8 tertiary hospitals, 6 community hospitals, and 21 physical examination centers. So there's a hierarchical level, not just in the primary care organization space, and also in the secondary care and the examination centers as well, which is pretty common in Asia. So what's the real value out of it is the study provides an important reference for the national medical products at the main in regulatory decisions about the new medical AI technology diseases. So on the right-hand side, that shows all the clinical settings and the locations has been tested, and including some abroad and cohorts in Africa, in Europe as well. So that study has been published in the Lancet Digital Health just a few months ago. So these are the details of the testing, the number included. But on the right-hand side, you can see provide a clear evidence either for the AUC or the sensitivity specificity curve. So the AI model is performed relatively well, at least to the equal quality of what these ophthalmologists specialists can offer, right? So these are based on large-scale study. If you are interested in AI models, so these are basically some technical overview and how the images are being used to train the model. So if you're interested, feel free to look up the table, the paper. Okay, so these are, if we're gonna, because we really want to do real world diagnosis and benefit the community. So if we really want to implement this model into the market, so what kind of steps we should take? What kind of component we need? So first, of course, you will need a fundus camera that has to be fast and continuous diagnosis by reading retina images. That's for sure. And hopefully that can be fully automatic. Then you just need an operator to operating the fundus camera, not a specialist, especially given that the ophthalmologist, especially in Australia, is way below demanding. Second part is you need a regulated AI model or AI solution that can do professional diagnosis of diseases in early stage. And the last part is how you present the results to the clients, to the clinicians is also as equally important by building a model because the report has to be comprehensive and easily readable, understandable, and provide evidence, right? So, the AI model part, of course, we get lots of data, we train lots of models, we do lots of validations, like exactly what we did for the care study in the Lancet paper. But for the fundus camera, I think that's more like only the solution commercial company can handle, because most of the desktop-based fundus camera are quite expensive. They are not mobilized, very hard to get sometimes, especially in the real world, in the remote region. That's why AI-powered fundus camera is a solution delivered by AirDoc. They have developed a very cheap AI fundus camera. It costs, I think, less than $1,000 US, around 800, 700. Can do quick check, also provide high quality of the images. And what's important, so the chips inside, it can connect to the cloud, or it can directly embed the AI algorithm into the camera. So basically, you can carry it to anywhere and do a retina scan for the patients on site, right? And if you care about the data privacy issue, of course, it can run on the cloud as well. So it is cost-effective, can do early diagnosis and early prevention, and do professional and accurate care. And that's the report part. So AirDoc has partnered in the Australian product. So AirDoc has partnered with iTelligence, so Melbourne here, to provide a product called Intelligence Assure. So this is normally what you see from the screen. So it's normally very user-friendly and traffic light system. So it give you better patient outcomes, etc. So these are the sample of the report information display. And these are some example of how many diseases being covered here. And so what I want to say is, as you can see, so from the lab environment to the real world deployment, there's a large gap in between. It's not just, I think, effort a university or research institution can handle. It's really important. You need to collaborate and work together with the healthcare provider, clinicians, and also the hardware, software companies together to deliver the final service. And now the service has been developed, deployed worldwide, not just in Asia, also in Australia as well. But that's based on numerous of publications in BMJ, in Nature Eye, in ophthalmology, and also in some full cohort study in China to provide evidence and backup. And all those papers, research papers in technology, in clinical study, they drive into the TGA and also the Chinese CFDA regulatory recognition. Okay, let me see the time. So how many minutes do I have, Jen?
You have as much time as you want.
Okay, maybe I will just spend 5 more minutes on this medical treatment, and then I will stop and take Q&A. Okay, great. So this is the work I written down with my collaborator, Professor Patrick Wang from the Alfred Health. So that part, the goal is to hopefully we can help to alleviate the issue of epilepsy or seizure, and using AI technologies together with the drug selection and to let the patient out of the seizure status as early as possible. So maybe a bit background, if you're a neurologist, you probably know this part very well. So what is seizure, what is symptom of a seizure, and how big the population is being affected by epilepsy in the whole community. So the number is pretty big, as big as the problem I mentioned in dermatology and ophthalmology before, and also creates a heavy financial burden as well. So the traditional way, if I understand correctly, is in the past 20, 30 years, first drug prescription is fairly important to treat the seizure status. But however, there are so many medicines being invented in the last 20, 30 years. So my collaborator, Patrick, has published 2 papers, one in New England Journal of Medicine, one in JAMA, to say, based on the cohort study in the past 20, 30 years, although there are so many drugs being invented, however, the first monotherapy seizure-free rate has not changed that much, right? Then that is because I think most of the traditional method of select the drug is more like trial and error, okay? So basically it means there's no reliable method to predict which medication would be most effective for a given patient. So for a newly diagnosed epilepsy patient, and anti-seizure medicine, ASM, is selected mainly based on reported seizure types or epilepsy syndrome, or more like a toss coin. So as you can see on the right-hand side, that's the figure from our recent published review paper from the British Medical Journal, BMJ. So the current method is more like a toss the coin, and then we give medication to the patient, see how it goes. More like trial and error. So what we imagine in the future, or the future trend, although this study is still undergoing, we're doing lots of research, is we think machine learning or AI maybe could help by using leverage more data from the patient and help to select a medication which is work more effectively or have more efficacy for the patients to take. So we try to jump out of the loop of the trial and error. So the physicians will be able to use the ASM selection model in conjunction with other factors. Yeah. So that's the overview of the model we're currently using. Maybe just give you a very high-level information. So we're using transformers by taking the patient's information. And the data we got actually is from multiple cohorts, not just internal and also outside external cohorts as well. So the information we want to include would be something like epilepsy classification, risk factors, medical history, demographics, EEG findings, so brain imaging findings, etc. So because that's the real part, we think machine learning can be very powerful. Because even as I said before, a well-trained clinicians cannot taking all the information at one time to make a correct decision. Maybe machine learning model can. I'm just saying maybe, because we're still gathering evidence and results to see if that's really the case. So we're gonna do maybe lots of trial in the future. So we have still study and going. So for some conclusions, some summary points, I think many come from my partner, collaborator, Patrick. As the first point is no change in overall seizure freedom rate despite 15 new ASM in the past 30 years. So current drug selection approach largely relies on trial and error. So machine learning has potential to harness the great ASM options for personalized epilepsy management. So I would say personalized medication, personalized healthcare will be the keywords, especially in the era of medical data digitalization. So we have trained and validated transformer model to predict response to individual ASMs for individual patients. So the results will be released in our next paper. So machine learning models must be rigorously tested before implementation. So these are also the point I want to bring. Is for the AI model in the lab to go into the real world, there's still a huge gap. The gap is not just in the model part, it's also in the testing, in the regulation part. So then we believe by taking all those factors together, full potential of neural ASMs may be yet to realize. Okay, cool. So I would like to thank again for all my collaborators, because I think medical AI is really a conjunction work from experts from different domains. So without these dermatologists, neuroscientists, ophthalmologists help, we can achieve nothing here. So I want to sincerely thank them again. And if you're also interested in working in the medical AI, or if you want to maybe get a more detailed story, or you just simply want to have a chat with our group, with me, if you are from a clinical background, you're very welcome to do so. All right, thank you very much. I'll stop sharing.
Thank you very much, Zhongyan. Really providing a very good overview of what you do and very proliferated result in many areas of medicine. We can now open our session for Q&A. If there's any question, please feel free to type your question in. I'll ask the first question, Zhongyan. In your first part, actually in the last part, when you mentioned that the AI can improve individualized management of epilepsy, that kind of, I think that individualized management kind of requires some knowledge of different patients leading to different results, kind of requires some good understanding of risk factor versus outcome.
Yep.
And at the moment, I can tell that by the fact that we have to toss a coin, choosing the first medicine is equivalent to like tossing a coin. We're not doing very well, sort of indicating we have a limitation in understanding the epilepsy very well. I wonder whether AI can actually help improve our understanding in epilepsy, because if AI can understand how to choose the first medicine, therefore achieve better outcome, I just wonder whether that can help us improve our understanding of the mechanism of the disease or the risk factor of the disease.
You mean more like a disease pathway, and how it's leading to some kind of different type of seizure. Is that what you mean?
I guess this is something that a clinician or medical scientist want to.
Yeah, I think so. I think most of machine learning model, AI model, they're data driven, right? And what they can understand, they can show, it cannot be beyond data. For example, if we only have the data of what kind of the medications the patient take, and also the patient's metadata, their clinical data, what we can show, the level is, so we get a model, and we see for some specific type of patient who can get seizure-free by using some medicine, then we backpropagate the signal into the input level. Then we can understand, try to show some correlations. If you are visualizing these kind of clinical factors, or you are observing some keywords from the MRI report or EEG report, these keywords maybe can link for some specific usage of the medication, which is more effective. So that's kind of level or maybe some observations, correlations, associations we can find. But if you are talking about the pathways, you need to go also deeper as well. For example, we now have the plan is to launch a project to understand the trajectory of some certain medications, how it bind to the receptor, how it cross the cell membranes, and work down to the pathway. So the data we have is trajectory, right? So we want to see so what kind of trajectory when they enter into the cell membranes will make the drug more effective. So this kind of level data learned by machine, then we can show the explanations from the machine learning model. So if you are talking more about the pathway understanding, we need kind of the pathway data to let the model to show that. Yeah.
So I guess we have a question here from Eddie. So there are many models out there, different models created from different data sets. For clinical physicians, how do they pick the right one to work with the AI model?
Oh, okay. So of course, okay. So there are many models, many data sets, right? Of course, your task will be very, very specific. I don't know which domain you're from, Eddie, but let's say if you are ophthalmologist, for example, if you're interested in AMD, then the data you collected will be the AMD data. But normally the model off the shelf on the market, or you can download with, it can be trained from other data sets. And these data sets cohorts and those risk factors and the age, maybe they have bias, will be very different from your clinicians and your working environment, right? So that's the reason why we say if we want to do, you really want to do serious medical AI model deployment, you need to have an engineer in your lab help you to adapt the model, fine-tune the model, transfer the model from a different environment into your environment by using your local data. You combine with the external data together, then you will get the maximum performance out of the model. I'm not saying the model probably won't work from the already well-trained model won't work on yours, but if you want to let it work better to realize full potential, you need to have this kind of like adaptation mechanism happening using your local data. Cool. This is my answer.
Yeah, thank you. It just really shows that the data, the AI learning is very data specific.
Yeah, that's right.
Actually, going back to my own question, we got a follow-up question from Professor Patrick Kwong, our collaborator mentioned in your talk. So Professor Kwong mentioned that in terms of the reverse engineering that we mentioned before, whether AI can help to improve our understanding of mechanism of epilepsy. Do you think this can be achievable if the models can be made more explainable? If we understand the black box issue a bit more better, do you think it can help to reduce the disease mechanism and identify the new treatment targets?
That's a good question. So probably one quick suggestion for Patrick, if you're still here, so you can check the latest publication from the DeepMind. So after they have building the AlphaFold model, basically predict the structure of a protein, right? So the next step is now they are using this alpha model to find maybe some effective or specific predict the effectiveness of the receptor, or what kind of receptor will the drug work better. I think it has nothing to do with the explainability of the model. I think when we talk about the transparency or explainability of the model is the model has so many different layers of projections, the parameters in the middle, right? You want to see how the model reach out to the final decision, right? But in terms of finding the new treatment targets, we have to rely on a completely different model mechanism. So most of the classification model, discriminating model, they won't work, and will be more rely on generative model. So the key idea of the generative model is you make predictions based on a probability space, right? Then the probability space maybe will represent your overall potential targets you can have. Then you can move around your cursor into the distribution and find one with highest treatment efficacy probability. So this might give you the answer of the target receptor, or maybe some new observation. But so far, the projects we've done so far is all classification model or discriminative model. It doesn't have this kind of mechanism to show what could be done, right? Or what could be the next target. It's basically showing what the target we have from our training set, what works the best. Yeah, so it's a different problem. I think it's more referred to the closed problem versus the open investigation problem. Yeah, but either way, if we want to make either way successful or more effective, we need numerous of data, right? Because the generative model is even more data hungry than the discriminative model.
Thank you for the word of wisdoms. Any more questions from the audience or from the panel? I'm going to ask another question. You mentioned that the AI algorithm is data hungry and also label hungry. And from previous session in this seminar series, I learned that you can get around with labeling the data. You can train an AI algorithm without labeling the data. Do you see the AI develop that way compared to AI developed with labeled data? Which one is better in terms of, is it like only a compromise so that we train the AI without label?
Yeah, I think you're referring to supervised learning versus semi-supervised or supervised learning. So currently, I probably maybe just tell you example of a semi-supervised learning where you have, let's say, 50% of the labeled data, and you have 50% of unlabeled data. Even the best state-of-the-art technology so far, there's a huge gap. So the best way to train a good model is you still need to train a supervised way. You need to have very good annotations. So unsupervised is even worse. I think our ultimate goal, of course, is seeking unsupervised. We don't need to label anything. We want the model to figure out the mechanism, to figure out the pattern by itself. It takes still a long way to go. I think most of the industry applications so far, classification model, segmentation model, autonomous driving, they are all supervised learning. I don't think there are a lot unsupervised learning, or there are no supervised learning at all. Yeah.
Thank you. Yeah, I was muted.
Okay.
Any more questions? I guess we are coming to the end of our sessions already. I just want to thank everyone for in the audience for joining in today. I really enjoyed the seminar. I hope you have. Thank you to our speaker and also Dr. Katerina Kieberg on our panel. Zhong congratulations to all the many achievements in your AI work. And you've done a great job today responding to all the questions that we throw at you from me and from the audience as well.
Yeah, this is my job, so it's fine.
Thank you.
Okay.
Yeah.
All right. Yeah.
I'll just add that we have our next session scheduled on Thursday, the 18th of November, 5 p.m. Australian Eastern Standard Time. The topic will focus on AI, how AI might aid the analysis of Stargardt disease progression, which is a genetic disease that causes progressive vision loss. And the speaker will be Dr. Jason Chan from Lion Eye Institute in Western Australia. And this will be open for registration soon. Just keep an eye on the website www.events.unimel.edu.au. And I hope to see you again soon.
All right. Thank you, Jen. Thank you, Katharina.
Thank you, everyone.
Yeah.
Have
bye.
a lovely afternoon. Bye.
Okay, bye.